So the first major optimization that I want to look at with our CPU, now that we've kind of talked a little bit about how we can change the organizational approach, we've talked a lot about how we can bring multiple instructions in at the same time and use an instruction pointer to decide where we are now. And now that we have a lot of instructions, hopefully that'll take out any gaps we would have incurred because of the time it takes to go to memory and come back. We've also separated out our actual execution part, so that can happen now synchronously with the fetch. And we even saw at the beginning how just doing something simple like adding a little bit of hardware, like a little adder near the program counter, means that we can increment it without having to lose a clock cycle to do that. Now we're going to look at a way to hopefully get us to what we would call a scalar processor. A scalar processor is a processor that can handle up to one actual instruction completion per cycle. Now, I'll talk about that because there's a little bit of kind of caveat with the star, kind of thing. The key is that you have to fill up the pipeline first, because an instruction that takes 4 cycles to complete still takes 4 cycles, right? I can't bend physics. I can't make things settle down in multiple places out of sequence at the same time, right? But the idea here is that we're going to build an assembly line that enables us to, in effect, be doing multiple things at the same time, so that even though each instruction takes exactly the amount of cycles it would have taken before, we're going to have multiple instructions in the pipeline so that one is coming off the assembly line every single clock cycle. And I'll kind of show that with some visuals, and I think you'll see that how that works pretty well by the end. So what we're going to do here is we're basically going to look for ways that we can take common operations that the CPU performs and engineer the CPU in such a way so that basically they kind of fall down this assembly line. They happen one right after the other. So we know we're going to have like a fetch portion of this. We know we're going to have a decode, right? Those we kind of have to do. We have to get the instruction, then we have to understand the instruction. Then we're going to have some kind of action. It might be the ALU, it might involve the registers, it might involve memory access, it might involve writing to memory. Sometimes we'll have something called a write back, where we have to take information that we worked with and then save it back to memory after we've worked with it. So there's going to be many parts that we could use. I'm going to keep things simple, and I'm going to kind of stick to either a diagram like this where it just says step 1, 2, 3, 4. I might use like fetch, decode, execute, write back, W. But just remember that there's no rule that says every instruction takes 4 cycles. This is just a way to kind of broadly explore the idea. Instructions take varying amounts of cycles. If it's a complicated instruction, if it's a floating point or something like that, it's going to take extra time for it to complete. So this idea isn't to say that all instructions need 4 cycles. I'm just using that as an example. So the way this works is you almost think of it as like a laundromat, right? If you have a home washing machine and dryer and you need to do your laundry, let's say you got 3 loads of laundry. Well, at your house, you're only likely to have a washing machine and a dryer. But you wouldn't do 1 load in the wash and then do that same load in the dryer and then leave the washing machine empty until the one is done with the dryer, right? And then put the second load in the wash. You would put the second load in the wash when you put the first load in the dryer, right? And you would at least get this done a little bit quicker than if you hadn't done that, right? Now, if you go to the laundromat, you're in a rush, you go to the laundromat and there's lots of open machines. You might just take your 3 loads and stick them in 3 different washing machines, right? And then stick them in 3 different dryers. This is exactly what pipelining is. It's no different. If we look down here, this is our timeline here. So at cycle 1 here, we can only do 1 instruction at a time. That's still important to remember. We can't throw these all into the pipeline at the same time, at least not yet. We'll talk about that more in a moment. This is our first instruction, and it's fetch, right? Now, when our first instruction goes to its decode, the fetch circuitry is available, so we put a second instruction into the fetch, or we get a second instruction, I should say, with the fetch. Now on time 3, our first instruction has been decoded. It's ready to be executed. Our second instruction that we fetched, we can now decode, and we can go ahead and fetch our third instruction. Now, sometimes there's something called a bubble in the pipeline. There's this idea that a instruction, either because of a dependency it has on another instruction or the complexity of the instruction, maybe it's a variable length instruction in this case, and the decode takes longer because we have to understand the length first before we can successfully decode it. Regardless of the reason for the bubble, they do happen, and they will have an effect ultimately on how much we can get done. In a perfect world, if there was no bubbles in this pipeline, we could get ourselves to the place where we are accomplishing one instruction per cycle coming out of the assembly line, so to speak, on the other end, right? And that's the important thing to remember here. In this case, we had a bubble, so this one's going to get pushed back another time slice. And you also have to take into account that the first 3 cycles here, nothing was coming out, right? So after you average this out and you get into millions or billions of cycles, that little bit in the beginning to fill the pipeline is called, doesn't matter as much. But there are some caveats. So what are the issues with this? Well, we can run into issues where what's called stalling. So that's because instructions might have a different number of steps. So if I put an instruction into the pipeline, and it's a basic system like we see here, and the first instruction that goes in has, say, 7 steps, and the second instruction has 4, well, guess what? They can both fetch and decode, but this second instruction is going to have to wait until this one is done executing, right? So that might be 3 time slots later. That will cause a bubble. It could be a problem from branching. Now, this is an even deeper problem because when you imagine what happens when you branch, right? Remember, when you branch, you change the program counter. So without any recourse there yet of trying to fix this, if I fill my program counter, or I should say that buffer, remember I go out and I fetch a whole bunch of instructions and I bring them back and then I have them in a nice order and I'm decoding them and those are going into the pipe. If I all of a sudden change which instruction I'm on, everything in that branch is now no good. Right? If I was on instruction 100 and I suddenly jumped to instruction 300 and I only had 100 instructions in my pipeline, guess what? I have to fill the whole thing back up. I'd start all over again. I have to go to memory, get instruction 300 and all the ones that come with it after it, and then I need to decode it and start over, right? Because that pipeline is now full of defunct information. So branching is a hard problem to solve here. We're going to talk about a few strategies for that in a little bit. There's also problems that we can have with data availability. So what if one instruction requires the output of another instruction, right? So imagine that you have 2 mathematical problems in your program. The first is a multiply because of order of operations, of course that would be, and the second is an add, right? So you have to do the multiply first, but the multiply takes longer, and not only that, but you need the result of that multiply to even do the addition. So even if there was hardware to avoid the bubble just based upon the different number of instructions, or if you had special hardware that could deal with a multiply hypothetically without it taking longer, you're still going to have to wait on the data to come back from the first operation so that it can be used in the second one. So what ways can we use to solve the branching problem that we just discussed? So there's a couple of ways we could do it. We could take a probabilistic approach. We could try to look at history and predict the outcome based on what happened. Now, this might seem a little far-fetched when it comes down to the hardware level, right? But it's actually not. And if you think about common programming circumstances, it might start to make sense as to why. So take a loop, for example. It is not uncommon for loops to take the same branch choice hundreds, thousands, millions of times before anything changes, right? It's a loop. That's what it's supposed to do. Even if you think of, you know, a for I equals 0 less than 10 loop for iterating 10 times, right? You still are going to be right 10 times until you're wrong the last time, right? So the idea here is just basically to use what is a very common outcome when you're programming, which is that there is a little bit of an ease of prediction. And this actually works fairly well, believe it or not. So another thing we can do is reorder the pipeline a bit. Instead of just assuming that everything has to happen in order, and this is a little bit of a slippery slope, we can actually try to be intelligent by looking as we decode at the instruction and understanding the nature of that instruction, like if it's a branch or if it's an add, and how we might be able to reorder things if there's no dependencies on data in order to kind of push the bubbles out. So if we have a really long operation, for example, maybe we can slip a few short ones in before, because we know that a bubble will happen if we do it after, right? This is a little bit of a slippery slope, and we have to be careful, because the von Neumann machine and in our architecture in general guarantees the programmer that their code will be, from their point of view, run effectively in order. Now, we're going to do a little bit of black magic, so to speak, under the covers, and it might not actually be run in order, but it has to appear as if it did. It can't offer any inconsistencies in the program. That is of paramount importance. So the logic to figure this out is really complicated, to actually figure out how we can decode things and maybe rearrange them in such a way that would lead to better results without messing up the program. Now, doing it this way also allows us to kind of explore our next step, which is to have parallel pipelines that might allow us to maybe do more than one thing at a time. So remember, we said scalar processing is this idea that our CPU clock is going to accomplish at least one thing per clock cycle, or at least we're going to get really close to it. That's a scalar processor, right? Because we have a pipeline and because we can keep all the hardware busy working on a different part of the process, just like an assembly line, that keeps everything moving, and it keeps us going forward, and we can hopefully get to the part where there's one kind of car, so to speak, popping out of the pipeline at every clock cycle, right? There might be 30 cars in the pipeline, but one gets completed at each step. That's basically the idea behind a scalar processor. A superscalar processor now is the idea that we can do better than that, and we'll talk about why in the next video.